Okay, so it's my pleasure to welcome Julia Julia Plavnik from Indiana University. She'll talk on remarks on the tensor product property for support varieties for finite tensor vectors.
Thank you, Scott, for the introduction. Thank you for having me at the seminar. It's a pleasure to be here. So I will talk about some joint work with Peter Berg and Sarah Witherspoon. This is a work that came in a series of papers, so I will remind you of some all the results that I mentioned in a previous seminar, but I will focus more on this tensor product property this time, and these are some papers that we posted last year, so I will tell you a little bit about that. So maybe I don't need to motivate this a lot in this crowd, because I think you all like these kind of topics, but in any case, I wanted to mention a little bit what is at least my motivation to study these kind of questions. So I started studying these topics from the point of view of Hopf algebras. So I studied for a long time Hopf algebras and then the representation theory of them. But at the beginning, I mainly focused on semi-simple cases. But then I was a postdoc in Texas A&M, and I talked a lot to Sarah, and we started thinking about non-semi-simple questions. So maybe I will say here in non-semi-simple settings, a lot of the things that I knew from the semi-simple, for example, when I wanted to classify certain tensor categories that were semi-simple, I could use a lot of kind of higher dimensional linear algebra. We like to say we could use matrices, we could solve certain things, but because we have this nice basis for the Grothendieck ring, and that was enough. But when you are in this non-semi-simple setting, sometimes you have different representations type, and you need to do something else. So in that cases, so when we were studying, maybe let me say we were studying the representation theory, or in general objects in tensor categories that I wanted to classify, we had challenges. We couldn't use the same kind of invariant. So we thought of going from this more algebraic setting to a more geometric setting. And in this case, what we started studying was this support variety theory that was proved to be very already helpful in the case of groups, right? And we did this going right through the cohomology. So these are the kind of things that I will comment about today. So maybe just as an example, and if anybody wants to ask me a question, please feel free to interrupt at any moment. I wanted to mention this category of representations of Hopf algebras, because I told you that's how I started. As a main example, to define later tensor categories in general. So I will start with a finite dimensional Hopf algebra. So in particular, I will have, right, the algebra structure, but also the coalgebra structure, and they are compatible. The comultiplication and the counit are algebra maps. And I also have the antipode, that it's this anti-algebra map, that in this case, since we're in the finite dimensional setting, it's an invertible map, okay? So in this case, for me, representations of H will be finite dimensional H modules, or finite dimensional representations of H. I will write it as H modules because it's a little easier notation-wise for me. And what I want to tell you are some nice structures or properties or things that I can do with this category, right? So maybe over K. Here for me, K will be always a field, and K will be algebraically closed. For me, sometimes you could ask for less, but I will ask for algebraically closed. The characteristic, in principle, I will not restrict it for now. So one thing that you can do is, if you have two of these finite dimensional modules, you can take their tensor product, and that's again a module over H. So we take the tensor product as vector spaces, but we give them a module structure. How we do that? we do it via the co-multiplication, and I will be using this Swidler notation. So I will act in each of the factors by the corresponding part of the co-multiplication. If you're not super familiar with Hopf algebras, that's okay. You can think of rep G for a finite group and think how you end up of similar things. In here, it would be, instead of this, it will be the diagonal action. So other thing that it's nice is that the field is also a representation in this case. And so how we will give the field the module structure. So in this case, we will do it via the co-unit. And so I will act kind of trivially how we will act via just applying the co-unit. And because this coalgebra is co-unital, we get that this representation via the co-unit, it's the unit for this tensor product that we define here. So if you tensor by K using this module structure, any W, you get that W back with the same module structure that you started with in any of the two sides. The other nice thing is that the dual of one of our modules is again a module. How? Here we will use the antipode, as you might have guessed. And also we will use the inverse of the antipode, depending if I want to give a right or a left dual structure. So how we will do this? So I will act on some linear functional of V. So to say, so this will be again a map from V to the field. So I need to tell you what's the value at certain element V in V. And we know how to act in V, so we will use that. We will use, okay, we know how to act by H in V, but maybe this is too naive. So what we will use is, we will use the antipode here. We will act by the antipode, and then we will apply F, and we will get something in the field as we want it. We could do this, or we could do the antipode inverse. If we do this, we will get the right dual. With this, we will get the left dual. In a categorical way to define it. It depends how certain maps are defined. But yeah, these are all nice things that we get in this category. And I wanted to mention them because that might be helpful to see the motivation when we define finite tensor category. These will be the main objects that I will be working with, and I want to compute and understand the properties of their support variety. So a finite tensor category over my field, remember this will be always algebraically closed. What is this? It's the category that has a lot of structure and also a lot of properties. The first structure that we want is that it's an abelian k-linear category. So abelian means just that we have direct sum, that we can basically do some, or we have exact sequences in our category, right? We have direct sum, we have kernels, co-kernels, we have the zero object. In the case before, we were fine because we were in the category of representations of a finite dimensional algebra. That's how we use the algebra structure in that case. And even more, since it was finite dimensional, it got some nice properties, so we will use that properties later in the definition. And k-linear means just that, so here, let me maybe say I have some zero kernel, co-kernels, etc. And k-linear means that the maps or the morphisms between two objects in my category, it forms not just a set, but also a vector space. So it has the structure of a vector space over my field K. And here's where the field is important. And when you're in algebraically close, it's nice because you have Schur lemma to use. That's one of the important parts where we use algebraically close. Other structure that we have is the one that I mentioned at the beginning when I talk about being able to tensor two modules and get a new module back. So my category is monoidal, meaning that I have a tensor product that it's associative via some associativity constraint, that it's unital. So this is a distinguished object in my category, that it's the unit, that this was the field with the action by the co-unit before. And to say that this is the unit, I need to say that tensoring by this is isomorphic to the original object. That's why we have here the left and right unitors maps. So these are the things, but here we have also a pentagon and a triangle axioms. So the triangle axioms is telling you how this and this are compatible, and the pentagon axioms are just, if you give me 4 objects, I have 5 ways to put parentheses on them, and that will be the vertices of my pentagon, and the arrows are all maps that we can consider with the associativity or the associativity tensor identity. So it gives you some coherence. This map is the map that gives you the change of parentheses. So if you give me 3 objects, there are 2 ways to put parentheses on them, and I know that they are isomorphic. This is giving me the coherence when I have 4 objects, and then that's enough to give coherence with any number of objects. Rigidity is what it came later when I talk about the dual. So what means rigid? That for every object in C, there exists right and left duals. When you're in a semi-simple category, this is for free. Like, for example, if you're thinking of algebras, they are semi-simple when S is equal to S inverse. So as I was saying, the left and the right dual in that category depend on S and S inverse. So in that case, they are isomorphic, but in general, they don't need to be. So we want to have both. And what it's a dual, I will not say it precisely, but it's another object in my category. But this is equipped with certain maps. One is the evaluation map. And the other is the co-evaluation map. This is very similar to what one could do in vector spaces. But always in category theory, we want them to be compatible with things. So we will have 2 zigzag axioms. This here, it's imposing some finiteness condition. For example, let me go back to my previous thing before. Here, I asked for finite dimensional H modules. It was not a coincidence. I asked for this finite dimensional condition. Otherwise, this condition of having left and right duals will not hold. So that's why I asked for that. Then the next thing that I will ask is that this, so for now what I did is I asked for some structure here and some other structure here. This is a property that this category has, the existence of duals, sorry. Then what I will ask is somehow a compatibility between these 2 structures. The first compatibility I should have said is that because I'm in this abelian setting, I want this bifunctor to behave nicely with the abelian structure. But the other compatibility that I have is that this object, which is an important object for the monoidal structure, it's also well behaved in the abelian setting. So what I will ask is that the unit for the monoidal product is a simple object. And the last condition is a condition purely in this part that I was mentioning. We have a finite dimensional of algebra when I started with. So I will ask that my category is finite. Finite means a couple of things. So it's a couple of conditions that I will have. I will require that my category have enough projectives, that my category, or that all the objects have finite length. I will also ask that the dimension, or maybe I will ask that I have something that I call finite rank. So what I'm saying is just finitely many simple objects up to isomorphisms. So for me, the rank is the number of simples. So I want to have only finitely many simples. And then the last thing that I will ask is, remember we have vector spaces here. I want these vector spaces to be finite dimensional. Okay, so these are our main main things or main objects that we will be working on. Examples to keep in mind are finite dimensional representations of a finite dimensional Hopf algebra, or if you want to think of finite groups, it's also a good example. Depending on the characteristic, you will have that it's non-semisimple or semisimple. When you're in this setting, and on top of this, you ask for semi-simplicity, or you have semi-simplicity, the category is called a fusion category. And there are other examples, but these will be the main examples that we will have in mind. So I wanted to tell you a little bit about these support varieties and specifically this tensor product property. So, and what it's motivating to us. So we will be working again with a finite tensor category. We always will work with this hypothesis from now on. And I will take some objects in my category. So some of the questions that we were thinking with Sarah first and then with Peter and Sarah were what kind of conditions we need on our category to have to ensure certain nice behavior with these objects. So in particular, one thing that we wanted to ask is when the tensor product being projective is the same, in one order, is the same as the tensor product being projective in the other order. Of course, if the fusion rules, which is the tensor product of the objects, are commutative, this will be true. In particular, if our category has extra structure, which is called a braiding, for example, rep G has the symmetric braiding, or could be endowed with the symmetric braiding, this will be true, but we wanted to know what happened maybe in the non-commutative setting. A related question is when or what need to happen for a power to be non-projective if the original object is non-projective. One comment is that if we tensor by projectives, we will be projective. That's why we are asking if it's non-projective here. And then this is kind of the question that I will focus on. It's what happened with the support variety of a tensor product. I didn't define support variety yet. I will do it in a little bit, but I wanted to mention these things. So the support variety, so we want to know when the support variety is the intersection of their varieties. So I want to, we would like to know what is the support variety of this. We would like to know it in terms of the support variety of these two. And there are certain evidence why asking about the intersection. I will tell you in a little bit. So we want to know when that is the case, when we can compute it as the intersection. So I will start introducing more now the cohomological background that I will use, but if you have any questions, please feel free to interrupt or ask me. Okay, in any moment. So I will just briefly mention what I'm considering to fixed notation and to remind maybe what is my setting, because different people consider different things. In finite tensor categories, there are different kinds of cohomology. This cohomology is more like a reminiscence of algebra cohomology, but there are others, David-Jeter cohomology and other things that are measuring different kinds of things, different kind of deformations and things like this. So again, for me, C will be always a finite tensor category over an algebraically closed field. Sometimes I will not write it. So we want to define some objects that we will be looking at. The first one is that I want to define X. So in this case, this will be just the equivalence classes of n extensions. Sorry, my handwriting, I hope it's okay. Maybe I should use this. Of X by Y. So what are for me these n extensions? Are just exact sequences in C that have Y. Then we have n objects in the middle. And then we have x. So I have y and x on the extremes, and I have n things in the middle. So this maybe n is here. And these are exact sequences in C. Okay? So now we can consider, using these extensions, we will consider the cohomology of C. It will be just in this case, the cohomology, in this way, which is just the sum of all the extensions between, or the self-extensions of the unit object for the tensor product that I mentioned before. So here n bigger or equal than 0. So in this case, what I'm doing are, I'm just picking 1 and 1. So I'm doing the extensions of 1 by 1. This is a This is a graded commutative algebra. And now we can consider something similar, but instead of self-extensions of 1, we could consider extensions of other object x, right? So it will be the same definition, but now self-extensions of another object. And this is actually a module over this one. So this is an HC module. And basically, I want to introduce a notation. Maybe let me say how this happens. So my handwriting was too big here. I will move this a little bit here. So the idea is that if we have one, okay, we have this map. Maybe let me mention directly the map that goes from here. Here, how I can do this, I can go via tensoring by x. So if I have one of my extensions, self-extensions of 1, now I can get a self-extension of x in the following way. I will just tensor by x all the sequence of x. So I'm here using this map that I just introduced. Okay, that it's tensoring, and this still, and this give me the action. Or I can use this to define the action. So something that, I cite Etinghoff and Ostricht because that's the conjecture maybe for finite tensor categories, but I have to say this conjecture is previous to this year in other settings and has a lot of history, specifically starting in groups. It says that, we are looking at this, or we can look at this algebra and we can look at the modules over this algebra, right? These specific modules. And the conjecture is that for any finite tensor category C, this algebra is finitely generated. And moreover, for any x, these are finitely generated modules. And this, I will use this notation, I will mention it here. I will say that if this is true for C, C has, or C, I will use the comment C with finite generation just because it was easier to write it in this way, but basically C satisfied this finite generation condition, let's say, okay? I will require this sometimes, so that's why I'm introducing it now. And as I mentioned, it has a long history, still very open, and I feel like this is a very interesting question. I will not get into the details, but I do like this studying the finiteness of these things a lot. So now I wanted to introduce what support varieties will mean in this talk. As a disclaimer, support varieties were defined in different settings. I will be talking about support variety for finite tensor categories. In the paper with Peter and Sarah, we also define it, instead of for finite tensor categories, for module categories over a finite tensor category. I thought that for presentations reason was nicer to introduce it just for finite tensor category, because any finite tensor category is a module category by itself. But what I wanted to say is that can be defined in a more general setting, and there are other settings as well that that consider these, that are also important. For example, there are people study this in triangulated tensor categories. Yeah, and as I mentioned, in the module category setting, but I will focus on this finite tensor category setting for this talk, okay? So my setup will be, again, a KF field, and let me write it here. I will be considering algebraically closed. Sometimes you can ask for less, you can ask for perfect or some other things, but I don't feel like it's so necessary. As I said, I will always consider C a finite tensor category, but I will ask that C has the finite generation, or satisfies maybe. Satisfies finite generation condition. Or the finite condition, generator condition is satisfied for this C. So the cohomology is finitely generated as an algebra, and the self-extensions of X are finitely generated as modules over the cohomology for any X. Again, another disclaimer here, this is not really a condition that it's needed, this one, but it's not needed for defining the support or for the most basic properties. But if you want to get really back nice homological information, you usually need to have this finite generation. So now, I was just mentioning before this map.
Can we ask a question here?
Yeah. I'm sorry, but Zoom usually blocks the sound, so I cannot hear. I know that you're asking a question, but I don't hear what you're asking.
Dan says that support varieties are developed at UGA. That was his comment.
Are developed at?
UGA here.
Yes, I know, yes. So I'm very humbling speaking about this. I'm a little nervous about speaking here with all the experts in the audience, and also the expert in different flavors of support varieties, but yeah, I know. And I might mention a little bit later, but yeah. So this map that I mentioned before, that gives the module structure, we consider this map, we have the module structure, and what we will consider is this two-sided ideal of annihilation. Two-sided ideal here. And we will use this ideal to define the support variety, okay? So what we will do is we will consider first of all, I will consider this, and I will define it. Usually we'll call this the variety of C, the variety of the unit object. The unit object is our distinguished favorite object for now. And what I will consider the maximal ideals in this homology. And then I will consider the variety of an object X in C, just as the maximal ideals, but now I will consider this annihilation two-sided ideal. So I will consider this quotient. Again, some other people consider different versions, even sometimes they consider prime ideals instead of maximal. We will stay in this case for now. So I will mention some nice properties. These are the maybe more basic properties that I was talking before. Yeah, that I think I mentioned in another previous seminar. But one thing that it's nice is that these support varieties, as in the case, a lot of these properties, maybe that's important, are properties, and many of these things, like tensor categories have a lot of reminiscence of groups or the representations of groups, as I was saying. And so a lot of the inspiration comes from all these things. So in this maybe more general setting of tensor categories, a lot of or all these properties that were proved for groups also work here. So the support variety detect projectivity. How? It's when the variety is 0. Then one of the structures that we were interested in was the abelian structure. So we want to know how can we express the variety of a direct sum, and this will be, in this case, via the union of the varieties. Then other thing that we are interested in when we're in abelian categories are short exact sequences, or exact sequences in general. And in this case, it's also something nice happens. The variety of any of these objects is included in the variety of the union of the other two in the exact sequence. So here, I'm using one of each of these in here. I'm not saying which is which, but the IJL is exactly the one right here. Then the other thing that it's nice is that if you have, and this is a result of Carlson in the other setting, but yeah, we use it as an inspiration, and actually we use a lot of, or we generalize to this other context some of that techniques that he developed. So if X is one of the indecomposable objects, which are something that for me are very interesting objects, because okay, with the simples we know more what to do, but when we're in this non-semi-simple setting, we need to have certain control within the composable. So what happens is that in this case, the variety is connected. And then this is kind of what I said before. We have some motivation to think about the tensor product property coming from the basic properties. The first thing that one can prove is that the variety in this order is included in the variety of the first factor. But now, of course, if this is a braided category, or it's enough that the tensor product is commutative at the level of the fusion ring, so the Grothendieck ring is commutative. You don't really, like braiding is an extra structure. You need to have commutativity in the fusion ring, but moreover, you need to have some hexagons happening. For what I'm saying, it's enough to say maybe commutative here, commutative.
I have a question.
Yes.
Isn't VC of X a closed cone?
Sorry, I cannot hear again.
A closed cone that would always be connected whether or not it's indecomposable. Oh, VC of X is a projectivization. Oh, okay, I'm sorry. Okay.
Sorry, I cannot hear well, but I think you figure out.
It was answered. We answered it. I guess.
No, I just didn't know.
Okay.
I missed the fact that it was a projectivization. So, okay.
Yeah, sorry. Zoom has this nice thing that blocks the environmental sound, but it's also hard when you want to listen to more people than the one that is next. So you can also write in the chat if someone is nearby too, so I can read. Sorry.
Okay, you can continue.
Okay. Good. So what I was saying is that now, if we're in the case where we have a commutative Grothendieck ring, this will be the same as Y tensor X, or isomorphic, right? And then I could have picked the Y here instead. So when we're in the braided or in the commutative Grothendieck ring setting, this is included in both varieties, so it's included in the tensor product, right? So let's talk about, I call it the main suspect, but I don't know if this was not a good joke, but I wanted to talk about this tensor product property because that's the title of the talk. So what we want to study is when this is the case, when there is an equality and not just the inclusion or what happens. So what we know, so I was mentioning this previous paper with Peter and Sarah, where we prove some of these conditions. Let me go back for a second. I don't want to be very, make people dizzy changing things, but when we prove, for example, this indecomposable result and also these things, so we also prove some realization result using special objects that we call, in analogy to the ones developed in the group theory case, Carlson objects. So if you have any of these Carlson objects that are defined in a similar way to the other ones, and we can talk more about that if we have time at the end and you're interested. In this case, if you pick X to be one of these objects and any Y in C, then the tensor product property holds. This was also useful for the realization of certain varieties, but doesn't matter, but it's also useful for this. So it's also true, we also know it for representations of certain Hopf algebras. For example, when H is co-commutative, there are results of Friedlander and Petzova, but there is also, maybe I should say here, results of for supergroups or super Hopf algebras or things like this. Here I wrote H commutative Hopf algebra, but yeah, there are other results. So Friedlander and Petzova. There are also results for some quantum groups. There are results from Chris Negron and also Julia Petzova, but also from Dan with Kent and Millen. So in the different setting, as I was saying, but there are also things where we know that this is not true. So, for example, we constructed, first, there are examples by Benson and Witherspoon. Sorry, I wrote it down. They computed some nice examples in positive characteristic. And then with Sarah, this was the first project where I started learning all this. We generalized these examples now in characteristic 0, and we also provide more examples in characteristic P. But what was important in this example is that in this case, C was not braided. So it failed more drastically. And I might say a little bit more of some things that I think about this. So maybe let me tell you a little bit about the new results that we have. So the first result is a reduction result. So we want to prove, or we want to know when this tensor product property holds. So what we prove with Peter and Sarah in the follow-up paper was that if you know that for certain class of objects that are in principle easier to work with, the property is true, then it's true for any other object. So that's one of the results. For that, I will need to introduce some notation. So I will introduce, or not notation, a definition, some notions. The notion of a periodic object in my category. So maybe to say it in words, a periodic object is an object for which, maybe I will say it, a minimal, the minimal projective resolution of X is periodic in principle of certain period, and this is measured by the CCG, so you get it's the same as saying this. Sorry, X, I don't know why I wrote them. Sorry, X. It's because when we develop, we use it module category, sorry. For some N. Let me see. This is just the image of the differential, the nth differential here. So that's periodic. So one of our results is related to this periodic object. It's also related to another definition that I might mention in a little bit. So what we proved was the following. So if you have a, I have my favorite hypothesis here, sorry. So if we start with a finite, but I will ask here for braided tensor category. So I didn't say what it's braided. Maybe I should say it in a minute. I mentioned more or less the idea, but I didn't define it, but I can mention it in a minute. So, or maybe I can mention it now. So braiding, so if C is one of these tensor categories, it's braided if I have that X tensor Y is isomorphic to Y tensor X, but this will be via some natural isomorphism that satisfies two hexagon axioms. That's what I said in words, but let me say what are these hexagon axioms. So the hexagon axioms basically are giving you the braid equation. Why they are hexagons and not triangles, which is more natural for the braid equation, is because we have associativity constraints and the unitor. So the idea is that we want this new structure that I'm adding on top of the ones that I have to be compatible with what I had, that was the tensor structure. So what I want to know is how to write the braid of a tensor product in terms of the individual braids. And there are two hexagon axioms because one corresponds to this side with the tensor product, the other with this one. But in the middle, when you try to write the diagram, you will need to do associativities. That's why are hexagons, okay? So I want to have a braided tensor category that is finite, also finite braided tensor category satisfying my finite generation condition. And then the following properties are equivalent. So one is just having the tensor product property for these things. For any two objects in C. The other is having the tensor product. So, I mean, the output is always having the tensor product property, to be honest, but what depends is that I will not ask for all objects in both cases. So this is for all X in C, and for all Y, maybe, yeah, of complexity 1. I didn't say what is the complexity. I might say in a minute. And again, here, I want for all indecomposable periodic, so these special objects here. I will also ask for indecomposable periodic objects here, and Y and Z. So in principle, the idea, we took a while to find a nice example where we apply it, because to be honest, computing, even the support for this, I mean, for this one, for the decomposable, it's not always super trivial, to be honest. It was not super easy, but we found very nice families of examples, specifically some nice SQ algebras. And we were able to prove this tensor product property for families. And in particular, we recover nice things. For example, the results that I was mentioning by Dubrovsky and Kujawa in the case of super Hopf algebras. In particular, with this, we can prove that symmetric tensor categories, symmetric finite tensor categories in characteristic 0 have this property. Symmetric is a special case of braiding. In characteristic P, it gets very wild because there are more things in characteristic P, but by the linear theorem in characteristic 0, symmetric is basically representations of a supergroup, and with a symmetric product with some exterior algebra. That's why these SQ algebras were nice. But we also recover some other examples in characteristic P that Julia Petrova and collaborators had. So it was a nice thing, but I want to say as a disclaimer that it's not like this reduction make it super easy. It's still computational challenging sometimes, and a lot of the tools that we use at the end of the day have some, it was non-trivial, I want to say, and it has some reminiscence of rank varieties that will be interesting to see more in detail what could happen in this setting, because rank varieties have a lot of the flavor of element-wide things that we cannot use in general for category theory, but in that examples that we were working, these skew algebras were fine. Yeah, but I wanted to mention that. I didn't say what the complexity, maybe let me say what the complexity is at least here. So the complexity of the object is it's the rate of growth. So maybe I will write this complexity of some object X. It's just the rate of growth. This gamma for me will be the rate of growth of the length. This is the length. This is the polynomial rate of growth. And you can define this using length or Frobenius-Perron dimension, but for some kind of things, it's usually better. Yeah, and P is the projective cover here. So we wanted complexity 1, and we proved to prove this, we proved some nice properties relating the complexity 1 with certain dimension 1 varieties and certain, and the indecomposable periodic object. So we did prove some other things here to be able to prove this. Sorry, I will pass this. I know that I'm kind of late on time, but let me tell you this is kind of the last part. I wanted to also tell you non-examples, because I said, okay, we know that this is true in some settings, and and if you see this also uses the braiding here, it's important. So I want to tell you the non-examples. So what we proved with Peter and Sarah in this other follow-up paper, that generalized some of the things that we proved with Sarah in a previous paper. It's related with this non-example thing. So we start, the setup for this is a non-semi-simple finite tensor category satisfying the finite generation condition. And what we can do is that we can always embed this one, embed it as a finite tensor category, into another one, into another finite tensor category. I will call it D, that also satisfies the finite generation. So it's interesting, the condition, but, okay, let me change this. No, it's fine. So if you give me this, I can always embed it in one that doesn't, but not. So it satisfies the finite generation, but not the tensor product property for varieties, for support varieties. So if you give me a non-semi-simple one with a finite generation, I can always find a new tensor category that has this as a subcategory, again with a finite generation, but not the tensor product. So let me tell you how we do it, because maybe that's more interesting. Probably there are other ways. This is one way. So what we did was the following. We started with a finite tensor category with our condition. This was a non-semi-simple, maybe I should say here, non-semi-simple finite tensor category with a finite generation condition. This C2 will be the multiplicative group further two. I'm just fixing the notation here. But the important thing is that this group always acts on the linear product of the two copies of C just by interchanging factors. Maybe here I need to say that when I say that, so first of all, I need to say this, the linear product, is the linear product of categories. It's like a generalization of the tensor product. So it's like a direct product of these two categories in some sense. So it has a universal property to define it. If we were in semi-simple world, just to have an idea, if we were doing C, the linear product D for two semi-simple categories, the simplest in the new category will be the product of the simplest, or like, yeah, the simplest given by a simple here and a simple here. So it generalizes the idea of the tensor product, and it has a universal property similar to that one. And this is a categorical action. So a group view as a category, and what I have is I have a tensor functor between this group and the automorphisms of this category. But the idea is that how it's acting, it's by interchanging this, it's by swapping the factors. When you have an action on a category, we can define a categorical action of a group in a category. We can define what we call the semi-direct product. Sorry. And that's what I will do. This is again a finite tensor category. So this is a finite tensor category with the finite generation condition, because this one had it, and because how it's defined, one can prove that this is still with the finite generation condition, but not the tensor product property in this case. Maybe just let me say something about the product in this category. So in this category, so how is the tensor product? If I have this, maybe H, what will be the tensor product? In the part of the group, it's just the group product, but in the other, what I will do is I will do like a semi-direct product. So to be able to tensor this with this, I need to pay the price of passing this through. So what I will do is I will act here by G. So basically, at the end of the day, this is kind of twisting the thing. So even if this category is braided, this category is not in principle braided. It's called something, or sometimes it's called G cross braiding, or in this case, C2 braided. So this is still not braided, and this is what it makes it fail having the tensor product property. So maybe to finish, I didn't wrote this, but one question is the tensor product property always, maybe not true, but always holds, but I already wrote it in this way, for braided finite tensor categories? This is one of the questions. And one other question that I have, it's like, okay, this is not braided, but it's G cross braided. Do we have some kind of crossed tensor product property, or some new version of this in this cross setting, which is not braided, but almost, can we modify this in some way that still makes sense to think of this as a cross tensor product, and now it will be true in these settings? Because usually all the examples that we constructed to make it fail was through this kind of deforming a little bit the product, like mixing it in this way. So I'm wondering if there is a way to solve it. So that's what I wanted to tell you, and thank you for listening.
So, hey, Julie.
Hi, Dan, how are you doing?
So we actually don't think that the cohomology ring is the right thing to use for finite tensor categories. This is in our paper, that's going to appear in Math and Allen. So we think that the central cohomology ring is actually the thing to use.
The second.
Yeah, so it's a subring of the cohomology ring. And you can
Mhm.
find supports on that, and it's much better behaved. And,
Okay.
and the idea is that that should control the tensor triangular geometry. And
Okay.
the Balmer spectrum should identify with the projectivization of that ring.
Okay, I need to think about. I saw that, yeah, that you mentioned something in the paper. I remember.
Yeah,
It's the paper with, yeah, I think I know which one. The non-commutative tensor triangulated geometry, right? Or
it's a third paper. It's actually has a tensor. Yeah, it's the third paper. And I think your question fits right in with our conjecture for the braided case.
okay.
So I think it's consistent with the conjecture, and also the examples that you have with Sarah, they all fit in with this, and they actually give you a computation of the Balmer spectrum.
Okay, but can you repeat? So you say it's consistent
Yeah,
because
so
you have this, it's this paper that you prove that the tensor product property with the datum, right? The support datum is equivalent to the primeness, or is not that one?
it's the paper after that.
Ah, the paper after. So I'm not thinking on the correct one. Ah, that's why. Okay.
So you may want to look at that, and I think it's
Yeah.
with
But
what-
what is the how can you repeat how this fits, or what's the
oh,
what?
because we predict what the Balmer spectrum is.
Ah, okay, nice.
The support data that you need to classify thick tensor ideals comes from
Yeah.
a subring of the cohomology ring.
The second. Okay, we'll look at this. Yeah, that's interesting. And yeah, one of the things we like is that you can compute the thick ideal. And I saw that in your papers, you can do a lot of interesting computation. I will check on the paper. Maybe I will write to you to ask you
Sounds great. All right.
more about that, but that's great. Yeah.
Let's thank the speaker again.
Thank you.